In my PhD, I'm now a PhD student here. I was a high school teacher, so I really like the teaching part. So yeah, it's also an occasion for me to practice my teaching. So yeah, today I'm going to talk about computer vision. So I basically divided the lecture in two parts because we have the morning and the afternoon part. In the morning, I'm going to talk mostly about object detection, and in the afternoon, mostly about image segmentation. Then I'm going to be here again next week. I believe it's on Wednesday. And I will mainly want to talk about multimodal stuff, so NLP and vision. And if we have time, also some 3D stuff, which is what I actually work on. I work on 3D representations for computer vision. But if you have like some kind of requests, feel free to ask. And if I have time and the expertise, I'll try to add them to the presentation for next week. All right. Okay, object detection. So you've seen convolutions, I guess, last week. So you probably are familiar by now on what they are. But the thing is, they're not born out of neural networks. Okay, so you have convolutional neural networks, but convolution is an operation per se. And I guess people that work in signal processing know it very well. So in general, if you have an input like this of any kind, and you have a kernel over there, which is also called filter. I'll probably call it filter most of the times. You can do a convolution operation, which just means sliding the filter over the image and multiplying the values in the filter to the values in this, I said image because it's mostly images, but it can be anything. And by doing this convolution operation, you reduce the dimension of the input to that output, and you compute some values for every cell in the output. But again, you've seen that kernels can be learned using backpropagation in convolutional neural networks, but this is not how they were born. Okay, so convolution is a general operation. There is continuous convolution in 1D, 2D, 3D, and there is discrete convolution as well. So in this case, it's clearly discrete. But yeah, again, the filters can be learned or can be handcrafted, all right? And in computer vision is a fairly old field in AI. So we started with the handcrafted stuff, but it's still relevant today. So I want to talk a little bit about it. So yeah, I mean, here I have an animation of convolution, but it's not particularly interesting. I guess you know what it is. And feel free to stop me at any time if there's something you don't understand. No worries, like no question is stupid. So just a remark, I will say convolutions and correlations interchangeably. They're technically two different operations, but for the purpose of anything we're doing today, they're the same thing. So we just take a filter and slide it over the image to compute the output values. Okay, that's it. Convolution and correlation doesn't really matter at this point. So as I said, we can have handcrafted filters. For example, we can have a mean filter, which has this shape. Okay, so this is a 3x3 filter, as you can see. And if all the values are 1/9, it means that we are computing the mean, okay, of the neighborhood of the pixel we are computing for. And if we want to have a bigger neighborhood, we can create a bigger filter, for example, a 5x5 mean filter. So here you have, of course, 1/25 in every location of the filter. For performance purposes, you can simply factor the division out of the kernel to be faster, but that doesn't really matter for today. And what happens if you slide the filter on an image in this case? So we have the original image and we want to corrupt it with Gaussian noise in this case. So you see, can you see it's noisy? I hope so. It's a little bit noisy here. You see like this is smooth. This is noisy because we added noise. If we slide the mean filter over the image, we get something smoother than the first image. So we lose some detail because we are applying a mean over a neighborhood, but we also remove the noise, okay? As you see, the noise is much less in this one compared to this. And in this one is even less. I can barely tell there's any noise, okay? But we lost some detail. Of course, there's downsides. Can we do something else? Like, are there any other cool filters? Yes, and they are useful. So let's see what happens if we have impulse noise. So in this case, impulse noise is just, you see like white dots and black dots. It's also called salt and pepper noise because it looks like salt and pepper. So if we corrupt the image with that and we slide the mean filter, it's still kind of bad. You see, we lose the detail, but we don't really remove the noise. Like we can still clearly see the noise here. It's mostly removed on the bottom right image, but it's still kind of there, and we lost a ton of detail. And the reason why we do not remove the noise is because this like white and black values are like 255 for the white in like 8-bit and 0 for the black, which is very different from the other pixels. So if we slide the mean kernel, that a single value is going to make a big difference for all the values in the neighborhood. So in general, it's not a very good idea to apply a mean filter in this kind of situation. So are there any other filters? Yes, so we can define basically whatever we want. One filter that is usually interesting is the Gaussian. So you've seen, I'm sure you're familiar with 1D Gaussians, 2D Gaussians, 3D Gaussians. You can have anything. So in the case of images, we will need 2D Gaussians. So we could take a Gaussian as a filter and slide it on the image. And we could do it continuously. What we usually do is that we discretize the Gaussian. So just like before, we had a 3x3 filter. Here we can have a 3x3 Gaussian filter in which the values in the filter itself are from a Gaussian. Okay. We can, of course, pick the standard deviation of the Gaussian to decide the shape. The bigger the standard deviation, the bigger the filter should be. Otherwise, we cut off all the values outside of the filter. It doesn't make much sense. We usually keep the filter so that the outside value of the filter keeps, I don't know, like 98% of the Gaussian or so. Yeah, we want most of the Gaussian to be represented in the filter. But yeah, anyway, we can discretize the Gaussian and apply it as a filter. And what does it do? What do you think it does? Any ideas?
Smoothing out the image.
Yeah. Yeah, exactly. So of course, the bigger the sigma, the more it's going to be smoothed. So we see it here. We have the original image, sigma 1, sigma 2, and sigma 4. So the bigger, the more it smooths the image. And it's basically a low-pass filter. So we only keep the low frequency features of the image, but we lose the high frequency detail, as you can see. What else we can do with filters? So up to now, we've seen linear filters, but we can have non-linear ones as well. So a median, for example, is a non-linear filter. So a median, we just take the filter, we check all the values, like in a pooling operation, like max pooling. In this case, it's a median. So we take all the values in the filter and we pick the median. And this is very useful for impulse noise. So this salt and pepper thing. Because if we apply the median, we are simply discarding the noise because it's out of distribution, basically. So it's very cool. You see, we retain almost all the detail and we remove the noise. So this is still very useful. And you can see like these filters are still used a lot. You can see them in Photoshop if you ever like used it. All of these are implemented in Photoshop and you can use them easily.
Can you explain why you applied the median, the same size kernel twice instead of using a lot? Or for example, so firstly, why did you use it twice? And secondly, how does that differ from using it 5 or 9x9? I'm not sure what the equivalent is.
Okay, that's a good question. So in terms of reach, like the amount of pixels it sees, 2 3x3 should be equivalent. Damn, I should run the computation. Not 9x9 for sure. So yeah, probably 5x5 or 6x6, something like that. I don't think it's exactly the same though in terms of the result. Usually applying the filter twice in the case of median is a better thing. In the case of Gaussians, I'm pretty sure there is a direct formula you can use. In the case of median, I don't think so because of the nonlinearity. I would need to check though.
Right, whereas a Gaussian twice is equivalent to...
There should be an equivalence to just applying it once with the right sigma. There should be.
Okay.
But yeah, also in general, we'll see it later. Even for convolutional neural networks, actually applying a small filter multiple times is beneficial compared to just applying a big one. Yeah.
Can just remind why we prefer using odd size filters rather than even size filters like 3x3, 5x5?
Yeah, it's because of the center. So a filter is computed like, if I go back here, here actually is better. So if we have this filter and we take a 3x3 here, we are computing a value for this pixel. Okay, the center. If it's 2 by 2, there is no center. You can do it, huh? You can, no worries. But it's usually better if you have a center. Like it makes more sense. But I think, yeah, there's a couple of 1 by 2 filters later that I'll show. It works anyway, but
yeah, but it works better with 3 by that I know. But
yeah,
center. Thank you.
no worries. Okay. All right, all good with the filters? All right. So edge detection, like we were getting closer to object detection, we first need to detect the edges. Do you have any idea of how to detect an edge? Like you can propose anything that comes up in your mind. So this is an example of an edge, right? So we have some part of the image which has this case one color or one intensity or one something that's kind of property, and another part of the image that has a different property. So how do we find the boundary?
We use the same filter, but instead of that, we will add some additional pixels with, let's say, padding 0 or something like that, and then after use the same like 3 by 3 filter size, and you have an edge of something, and you don't have a pixel in the rest of the things. You just add 0 in them, and then after move the filters just like that.
So I'm not sure to understand. Let's say this is a big, very big image, and the filter is very small, like here.
Yeah, just like imagine like we are applying filter to the first line of the image, a 3 by 3 filter, and it's kind of covering like only first 2, and rest of the 3 by 3 filter is like empty. You cannot cover it because there's no image. So you just pad the image with the 0, 0, so that you can actually detect even the edges with the filters.
But I'm not sure how the padding has to do with the edge detection. So I'm just talking about some edge inside the image. So there's no padding involved. We're not out of the image. I want to detect an edge inside the image.
So it sounds like differentials where you want to see the contrast, like from the dark and bright.
It's absolutely differential. Yes. Yes.
You can't just use straight ones on one side and then minus ones on the other side?
That's one way to do it for sure. Exactly. Very happy you got this. Nice. So what you can do is literally compute the gradient of the image. So you compute the partial derivative on the x-axis, the partial derivative on the y-axis, and then you get the gradient. And the way you do this in an image is, since you have pixels, you cannot compute an actual gradient, but you can use finite differences. Okay, so you have pixels. So we can approximate the partial derivative on the x-axis by pixel difference, and same thing for the y-axis. And you can do it as a forward or a backward difference. Okay, it doesn't make doesn't make much difference. So you can either pick the next pixel and subtract it, or pick the previous pixel and subtract it. It's the same. And these things you can implement as filters. So like you said, you have a -1 on one side and a 1 on the other side. Okay. So this is a 1 by 2 or 2 by 1 filter that you can convolve over the image to get another image that is actually the gradient. You get two images. One is the x part and the other is the y part of the gradient. But you put them together and you can get the direction and the magnitude of the gradient. You can do a similar thing with central differences, and this is what we usually do in practice because it's more stable. So to compute the gradient at a certain pixel, you get the previous and the next, but you not take the pixel into consideration itself. And this is also odd, so you can actually have a center of the filter again. So since having like this kind of filter, if you have like a very clear edge, like I showed in the example before, it's very easy to detect with this filter. But what you want to do in general is have some kind of smoothing. So you want to compute the gradient over a bunch of pixels, not just one before and one after. So what you do is that you can apply a mean filter and a gradient filter at the same time, but in opposite directions. Okay. So here you have, for example, the first one here. So you have that the gradient is computed on the x-axis and the mean is computed on the y-axis, okay? So it's opposite directions. They do not impact each other because it's the perpendicular, sorry, not opposite. But it's very useful to approximate the gradient, okay? So this is what is usually done. Same thing for this with inverted axis. And if you use central differences instead of forward or backward, you get the Pruitt operator, which is well known. And if instead of using all ones, you weigh the central line more. So you have a 2 here. Then you get the Sobel operator, which is probably the most used operator for edge detection. Okay, and it's still used nowadays. You can still use Sobel to do edge detection nowadays, and you can use it in conjunction with neural methods as well. Okay, I'll show it later. Any questions on these? Oh, all right. Wait, let me check the time. Okay. All right, so what do we do once we like do this convolution of the filters on an edge? So if we have an edge like this, and we take, let's say, a Sobel operator on the, let's take the X part of the Sobel operator. So we will have some values. Let's say here we'll have value 9, here we'll have value 40, here value 8. Where is the edge? Okay, we look at this and we can clearly see the edge. Okay, it's 40, 42, 40, 44. So the edge is here in the middle. So we have to tell the computer how to detect this. And this operation is called non-maximum suppression. I will not go into details, but it is very briefly how it's done. So if we already know the axis, it's very easy. So we follow, let's say we take this row, we take 9, 48, and maybe a few more values on the left and a few more values on the right. And then we take the local maximum of them, okay, to get the actual edge, and we discard the rest. But the problem is we do not know the axis beforehand. So how do we do this? And what we do is that we, since we have the, so this is the X derivative, partial derivative, and we have another image with the Y partial derivative. So we have the direction of the gradient for each pixel, okay? The direction of the gradient will tell us the direction of the edge, okay? Which is perpendicular to the direction of the non-maximum suppression operation, okay? So if the edge is in vertical direction like this, we want to perform non-maximum suppression on the horizontal axis, okay? If it is diagonal, no problem. We can simply linearly approximate intermediate values between pixels, and so that we have these gradient values in non-pixel positions, okay? So we approximate the a continuous image by linear interpolation, so that we can do non-maximum suppression along any axis, okay? It doesn't have to be X or Y, it can be anything. I know it's not super easy to understand. I don't want to go in the details, but we will use this operation in the code. I'll provide you the a function to do this, just so you know that this happens. Yeah. So it's a finite difference. So if you have, so you know, let's take just a differentiation in one dimension. So you have derivative, you have is the limit for the delta x that goes to 0 of the difference between 2 points in a function divided by the delta x, okay? So if you take the limit for delta x that goes to 0, you get the actual derivative. If you don't make it go to 0, you don't have a derivative, but you have an approximation of it up to a certain degree. And here we don't have a continuous function. An image is a discrete function, so we cannot really compute a derivative. But what we can do is compute this finite difference gradient. So you can see the gradient as just the difference between 2 pixels. In this case, the delta x is 1 pixel, so it's 1. So we don't really care. Or even if it's not 1, like in this case, the delta x is, you can see it as 2 pixels if you want. But it's just a normalization factor. We don't really care about the denominator. All right. So what do we get with the Sobel operator? Yeah.
Are you going to get into more detail with these non-vertical, non-horizontal lines?
Was not my intention, but if you want me to.
So then it's the right time to ask.
Yeah.
How do you know which angle you want?
So
do you have to just compute every angle?
No, simply, okay, let's say we want to perform. Let's say we want to perform, we are in this pixel, we want to know if this pixel is a maximum or not. Okay, so this is an operation we compute for each pixel. So we are at 42, we want to know if it's a maximum or not. So we take that pixel and we get the gradient, the full gradient of the pixel. 42 is just the X derivative. We want the Y derivative as well. We compute it with another Sobel operator on the other axis. We get these two, so we have the full gradient, which gives us a direction. We normalize it and we get a direction. Okay, that's the direction of the gradient.
No.
Right, so that's the direction we use So this is the direction of the predicted edge. The gradient is going to be perpendicular to it.
Okay.
And we perform no maximum suppression along with it. Okay. So we get this, the intersection of this direction with the grid gives us this and this positions, for which we compute the derivatives as a linear interpolation of the nearby pixels. Right. Okay, so what do we get? As you can see, this is an example result for subtle edge detection. This is actually an image from a currently used data set, so it's not something particularly simple. It's also not something particularly hard, because as you can see, there's a stark contrast between like this man on the foreground and the background, as well as here, like the tripod. There is a bit of contrast. Of course, the less the contrast, the more difficult it is for a gradient-based operator to find edges. But it works. It works very well. And of course, you can post-process this image to maybe remove some edges that you don't want and stuff like this. But it's still a very useful operation that you can use without having to train it. That's kind of the point. Okay, so you don't have particular data to do this kind of things. You can train it to do this. And I'm not sure I have more examples. No, I don't. But I've seen it used in practice in like cell detection algorithms, because they're usually, I mean, the images I've seen, I'm not sure if they're always like that. You have like a pretty good contrast between like cells or mitochondria or stuff and the rest. So it's not easy to find, but it's not like they usually didn't look like an image like this, in which maybe you want to find like these edges or stuff like that. But it might have been like a simplistic case. So I don't know what the kind of images you guys see. Okay. They're harder. Yeah. All right. So we'll need to use a different method. So a little spoiler on the CNN filters. So if you take a convolutional neural network that's been trained on some kind of task, let's say classification from images, and you take a look at what the filters of the network have learned, like they look like subtle operators to me, right? Along different directions. Some of them are horizontal, most of them are diagonal in some kind of direction. They compute more or less derivatives, okay? It's not precise, it's what they've learned, but they are basically edge detectors. Okay. All right. Any questions on this part? Because I will move to a slightly different topic. All right. So half transform. So let's say now we have some edges, but what we want to do is we want to get the line the edges belong to. Okay. Let's say we are like a car on the road, and we want to find the white lines in the road. Okay, they are lines most of the time. So we can use some edge detection operation, some segmentation operation to get some pixels that belong to the lines. But then we want to get like an actual line out of them. How do we do this? And there's a classical method to do this. It's not deep learning based, but this can be applied to deep learning too. I will briefly show it later. So let's say you have a line equation. So y equals mx plus c. So if, let's say you have this point here, okay, 1, 1, there is infinite lines that pass through the point. Actually, let me use the pointer so that people on Zoom can see as well. So you have infinite lines that pass through this point, and you can express them as, okay, or you can plug the point coordinates to the equation. So we'll have 1 minus m times 1 minus c equals 0, okay? So you have, how do you say it in English? Like the bunch of lines. Damn, I learned this in Italian. Huh? Family, maybe. I just realized I learned this in Italian. I don't know how to say it in English. Okay, anyway, you have a family of lines that pass through a point, and same thing for the other point. So if you have 2 points, maybe I can write it quickly. It's clearer. Can you see my like iPad screen online? I'll take it as a yes.
Line is fine.
Okay. So let's say you have this point P1, which has coordinates 1, 1. So if we want to plug it to like a line, we will have 1 minus m minus c equals 0. If we do the same for the point 2, which has coordinates 2, 3, we can get, is this 3 minus 2m minus c equals 0. Okay, so if you want to find then, of course, the line that passes through both points, an amazing, very straight line, we will need to solve the system, okay, for the two parameters. Easy stuff, nothing new. But what if we go in parameter space? So if we take the first line, 1 minus m minus c, we can see it as a line in the parameter space. So it's not a line in the xy Cartesian space, but it is a line already in the parameter space, okay? And it is this line here, okay? This is the line that represents all of the lines in the Cartesian space that pass through point P1, okay? So this is a parameter space. You can see on the x-axis we have the m, so the angular coefficient, and on the y-axis we have the y-interception. So we can change the m and the c along this line, and we'll still get a line that passes through point P1. Does it make sense to you? All right. Same goes for the other line for this one. So this is all the lines that pass through point P2, and the intersection of these two lines, so this point here, is exactly the one line, this one, that passes through both points. Okay, so one point in the parameter space is a line in the Cartesian space, in the image space, and vice versa. Okay, so this is very useful to detect lines. Let's go back here. It's very useful to detect lines because let's say we have a bunch of points around here, and we want to detect the line that passes through all the points. We can go to parameter space, plot all these lines, and see the area. Of course, in this case, it's precise because all of these points lie exactly on the same line. It's not going to be so precise, but there will be a region in the parameter space that will have a lot of like close points and close lines. So that region, that particular point in parameter space, will correspond to a line in the image space that passes around these points. Okay. And the way we do this in practice is that the parameter space is parameterized by an accumulator array. Okay, so it's not a continuous space. We want to do it on a computer, so it's discrete. We discretized by this AA, which stands for accumulator array. So again, every point on the image space will vote for a line in the parameter space. So let's say there is a line that goes from here to here. Okay, this thing. That point that corresponds to this line will vote +1 on all of these points. Okay, and as you can see here, we have some maxima. So this will be the line that corresponds to the image space. Does it make sense? Okay. In practice, just a note, we do not use the M and C for the accumulator array. We use the theta, which is the angle of the line, and the R, which is the distance from the line to the origin. The only reason why we do this is because M and C are unbounded. So it's not easy to get an accumulator array for them. Instead, the angle, of course, is bound, and the radius is not bound. Well, let's say it's bound by the image size. Okay, it cannot be higher than the image size. So we have a precise bound for both the angle and the radius. So we can use a discrete accumulator array on them. So instead of being lines, they will be sinusoids. This is the only difference, but it's exactly the same thing. And we can do the same thing. So this is for lines, something very easy, but we can do the same thing for anything, okay? As long as you can express it via an equation. So you can do it for circles, for ellipses, for basically anything. And there is also, wait, let me skip these for a sec. There is also a generalized version of the half transform. I'm not going to it, but you take any shape and you can do this, okay? Absolutely any shape. Take this, you construct a table, accumulator array with some parameters, and you get what you want. but again, I'm not going into detail for that. You just need to know that a half transform exists. So the way we can use it is that if we have an image and we get some contours like this via edge detection, okay, of course, this is a very simple case, then we can have these contours to vote in the accumulator space, and the maxima in this space will be lines in the original image, okay? Then we can see what are the voters of a specific line. So all of these voters will belong to that line. So then to get a better approximation, we can use least squares on those voters to get a more precise line, okay? Because this is a discrete accumulator, so could be not too precise. So usually we run least squares after the half transform. But this is the general idea. And we can use it on real images as well. In this case, we can find the lines for this sign on the road, for some other things, not particularly interesting in this image, but much more interesting on this one, okay? So we can fairly easily find lines like this, already with classical methods. Road edges as well. This is also something very useful for automated driving, because you need to know not just where the lines are, but where the road edges are. And it's usually, you can usually find it using half transform. Not always, you see this is not very good. But you can use it in conjunction with deep learning. So let's say, so this is an example of a drone that navigates an aerial environment, and you want to avoid the electrical lines. But electrical lines are super thin, that you can barely see them in the images. So it's not that the half transform is going to be able to see them and find the lines, but if we train a neural network to see them, then we can use, instead of the half transform on the image space, we can use the half transform on the feature space, okay? So we take the feature maps out of the neural network, and we can apply the half transform to them. And then what in this paper do is that they use some other convolutions in the half space before going back to the image space. But anyway, it's just extra parameters. The point is we can apply the half transform. It's still applied nowadays on convolutional neural networks. So this is still something that you can do. All right. Yeah. No worries.
Matrix we get from doing like the finite distance.
You can apply it to anything. So I've applied half transform directly to images, just like that. You can apply it. You can first apply some edge detection algorithm and then apply half transform to make the half transform easier. The edge detection can be a Sobel filter, can be a neural network, can be anything. Or you can do something like this, in which you do not apply the half transform on an image, but on features directly. So in a sense, you can see that an edge is a feature of an image. Okay, so instead of having an image, you have something that resembles an image, but it's just the edges. Okay. If we go in neural networks here, this feature maps will not be anything in particular, but will contain some information. Sorry, that's the point?
If we apply it like directly to the example, sure.
Yeah. Oh, yeah. You always have to, yeah, that's a good point. You always have to apply some kind of thing to get what points will vote. Some kind of filtering you need to do beforehand. Can be edge detection, can be some thresholding, for example. You can say, oh, only the pixel with certain values would need to vote. Usually it's something complex. You don't really apply it directly because you want some information to be extracted first. Yeah.
I'm also making the assumption that these elliptic lines are completely straight lines.
Yeah, that's an assumption if we use half transform for lines. I guess for this paper it was enough. Taking into account that finding these lines is still a very challenging task. There's research going on nowadays. It's not a solved task at all. Okay, it's super hard because you cannot really see them. So what networks should do is they should learn some priors for which, when you see electrical poles, there will probably be electrical lines in between. And what is the shape of these lines? they are mostly straight, but they're of course impacted by gravity, so they have some kind of paraboloid shape. You can use half transform for that as well, if you want. I think they use line half transform in this paper, but you can use something else, like a different half transform. But it's a super hard task, especially because the annotation for these datasets is super hard. You see that even in the I don't have an example here, but in the annotated images, the the lines, like sometimes you see the lines, but they're not annotated, or sometimes they're annotated, but you don't see them. So you're like, are they there? Are they not? Sometimes they're not precise, so they maybe shift a little bit. So it becomes hard for the network to learn the prior about the electrical poles. Is not an easy task, and as most of the times, it's more of a problem of like human annotation than of the model themselves, like quantity and quality of data than the model themselves. But yeah. Okay. So early object detection very quickly. So if we want to detect an object in an image and we have the object like this one, we can use template matching. What is template matching? Well, we basically take this as a convolution filter and we slide it over the image and we compute some correlation function between the filter and the image in each position. And then we only take the positions that have a sufficiently high correlation, maybe using also some non-maxima suppression if we want to. And it's very easy to find templates like this in images like this. But of course, this is a very simple approach. Okay, so what if the object is rotated? We cannot find it like this. What if the object is like tilted or slightly different or a different color? It becomes really hard really quick. So what it is, it's just a manually defined convolution operation. So again, it's not particularly interesting. So we know neural networks can do convolution, and they can learn the convolution instead of doing it ourselves. Like, why do we have to handcraft stuff? So let's let neural networks learn the convolution by themselves to find some interesting information in the image. So to do this, I want to start with ImageNet. So ImageNet is a data set that's been released in 2009. So it's a fairly old data set, and it's considered solved nowadays. I think it's been basically solved by some definition of solved in 2015 or 16, depending on what definition you choose. But the point is, in this data set, you have a ton of images, and each of the images is labeled with the object inside of the image, object or animal or whatever. So let's say these are images of dogs, these are images of working dogs. So the classes of these objects or animals are quite specific. And the goal is, like the creators of this dataset introduced a challenge, like you have to produce the best model that can have the best classification accuracy here. So we're talking about object detection. We want to detect the objects and the animals and the items inside the images with the best accuracy possible. And the way object detection has been done using neural networks up to that point was sometimes convolutional, like in this example, the LeNet from 1989, the first iteration. This is a very famous approach introduced by Yann LeCun, which is, I guess you all know Yann LeCun, but is a super famous researcher in the AI field. And the thing is here, he basically applied for the first time backpropagation to convolutional layers. Okay, so before that, backpropagation was applied to fully connected layers, not to convolutional layers. He did it to convolutional layers, but the problem is, so this is an approach that worked. It worked nicely, full stop, but it was very slow. Okay, CNNs are slow compared to fully connected layers. The cool thing about CNNs, as you've probably been told last week, is that they have less parameters compared to fully convolutional layers to get the same feature space out of them, but they're slow. Okay, they're still slow. And since you usually work with images, they're particularly slow because the input is very big. So in general, it's not easy to work with CNNs, or at least it was not easy to work with CNN. A big revolution came in 2012 with AlexNet. So AlexNet, Alex is the name of the creator, Alex, this guy. And you might recognize Ilya Sutskever and Geoffrey Hinton as the other authors. Yeah, like cool people. So it's 2012, NeurIPS, So very, very famous paper. It's probably one of the most cited papers in computer vision. I think it has like more than 100K citations or so. Crazy stuff. Absolutely crazy stuff. So the cool thing here is that they implemented CNNs on GPUs. Okay, it's not the first ever implementation on GPUs. It's a good one though. And they also like changed a bunch of other things to make them work a little bit better. So that's how the breakthrough came. And I mean, it's kind of similar to what happened with transformers, right? So the breakthrough arrived first with the introduction of the transformer architecture, and then with the creation of huge data sets that you can train it on. Okay, what do we have here? New architecture, fast in this case, and in a big data set to train it on. Okay, it was a super major breakthrough, like comparable to what you have today with ChatGPT. Maybe not as impactful for the general public. It's not that they released like an app in which you can use AlexNet on your phone or stuff like this, and you can talk to AlexNet for sure. But it was impactful because it basically started a big line of research and a ton of money from companies that they wanted to invest on this because finally it worked and it was doing something useful. So it's really, really important. So what's AlexNet? It's very simple, actually. So you have a convolutional neural network, plain old convolutional neural network. There are like 1, 2, 3, 4, 5 layers. So it's not even particularly deep, but it was deep for the time. And the way they achieve this kind of depth is because they use ReLU activation functions, okay, instead of tanh or sigmoids or anything else. And the reason because they use ReLUs is to avoid the vanishing gradient problem, okay, because in the ReLUs the gradient is 1. So that was a very big part of it. Then they use also some max pooling operation that I'm sure you're familiar with. And compared to some like almost contemporary approaches, they use dropout as well as regularization. And it turned out to work very nicely. They absolutely destroyed every other method. So they achieved a top 5 error of 15% on ImageNet, which is crazy. Was crazy for the time. Top 5 error means that the network outputs 5 classes, possible classes. And if the actual class is one of the 5, it's good. Okay. There is a more strict evaluation, which is top 1 error. So the network just gives you one class, and that should be correct. But we usually evaluate with top 5, especially because if you look at some, why do I keep clicking? If you look at some of these, like this dog gets a dog, there's cherries as well. Like, what's the actual answer? What do you want me to say? So it's usually good to have a few classes output by the model.
How many classes are in the problem, roughly?
In the data set? I don't know. Good question. Let me check. So yeah, 15%. And I think the human error on this data set is around 5% or so. So it's still far from human error, but it's getting closer. Here's just, I mean, the detailed architecture for AlexNet. You can see it has the 5 convolution layers, 3, yeah, 1, 2, 3 max pool layers, and 3 fully connected layers in the end, 62 million parameters. So it's, I mean, small for today's standards, but it's not really that small. Here's some results that you can see. It was mostly very good, as I said. Motor Scooter, Leopard. This one, I mean, it's supposed to be Cherry, the actual class, but the model predicted Dalmatian. So it's actually correct. It's difficult to say it's not. Yeah. Yeah. Yeah, since 2015, networks outperformed humans on this task. And I think here it's very small to see, but it's more or less 95%, the human line. So yeah, 5% error for humans. Yeah, and as I said, like in the spoiler I did before, so here are some feature maps extracted from AlexNet, and as you can see, they're basically solver filters. Like they do get some gradients, and in the deeper you go, the more complicated the filters get. Okay, so here they just detect some kind of gradient on some direction, some derivative on some direction, and here in the second layer they get something more complex. Okay, you see this like circle things. I can't really see from here, but they will probably start looking like parts of the object that the network is supposed to detect. Okay. And yeah, apparently the brain is also believed to do something similar. I don't know, I'm not a brain scientist. Yeah, okay, I added these reminders, but they're probably not useful. We just saw them. Okay, so what next? What's after AlexNet? So this is VGG. This is so while AlexNet was a breakthrough, but is not really used today anymore, VGG is still used today. It's fairly old, 2014, but the reason why it's still used today is because it's fairly fast. Okay, so I still see many papers using it in research nowadays. So the main idea of VGG is that they want to achieve higher depth, which was thought to give better accuracy and actually does give better accuracy. But they didn't really want to increase too much the number of parameters or even increase too much the reach of the filters. Okay, like the deeper you go, the bigger the reach of a filter, right? Like you keep applying a filter and the bigger the more pixels it reaches. So their idea was to apply small kernels instead of AlexNet that has like some 5x5, 7x7 kernels, and then some 3x3 kernels. In VGG, all of the kernels are 3x3. Okay, super small. But the network is deeper. Instead of being 5 layers, it's like 16 or 19, depending on the version. So much deeper. But the architecture is not complicated. So there's convolutions, ReLUs, max pooling, some fully connected layers, and the softmax in the end for the classes. Oh yeah, 1000. It's over there. The number of classes. So yeah, here's a detailed architecture. As you can see, it's more parameters. This is VGG 16, so 16 layers. As I said, there's also VGG 19 with 19 layers. And all of the kernels, as you can see here, are 3x3. Okay, max pool is 2x2, but the kernels are 3x3. And you can see here, so instead of using bigger filters, so if this is the output feature, this is an input feature. If we slide the 3x3 kernel on the input feature, we get the value for this point. And if we slide here, we get this point. Here, we get this point, and so on. And if we get this and we apply again a 3x3 filter, we get this output value. So we have that the 3x3 two consequential 3x3 filters had a reach of 5x5 in this case, to answer to your question as well. Yeah. Any questions? Check the time. Okay. All right. So after that, what happened? So we tried to go even deeper. So as I said, VGG 19, 3 weeks of training, Google Linet, it's around the same depth, I believe. But yeah, I mean, the deeper you went, the better it seemed to perform. And another kind of revolution arrived with ResNet. I think you also saw some ResNet in the first week, I believe. Did you? Yeah. So in ResNet, as you probably remember, you have skip connections from one layer to another. And this helps even more for the vanishing gradient problem, okay? Because if you skip the connection, then you skip also the gradient computation. And it makes it much, much easier to reach very deep architectures. So ResNet is super deep. So the shallow ResNet is 50 layers, and the deep ResNet is like 150. So it's much deeper than the previous architectures. And this is also still in use today. I still see it. It's slower than VGG though. So depending on the application, one could want to use VGG, losing some accuracy, but gaining speed. Okay, it's a trade-off. Yeah, you've probably seen this as well. So without the skip connections, here we have that 18 layers. So this is a loss function, and actually an error percentage with the iteration on the x-axis. So an 18-layer network starts learning and keeps learning until kind of plateauing it here. 34-layer network is basically the same. Okay, there's no improvement. Actually, it's a little bit worse. But if you use a ResNet, so use the skip connections, then you get something better. 34 layers, and then it keeps going. 50 or 150. Yeah. Who annotated the data? Yeah, that's a good question. It's there's more than one annotator per image. So the network tries to learn the most common annotation from the annotators, whereas a human might make a mistake because they might want to do another annotation for that image. So saying that networks are better than humans is always a little bit of a stretch, in my opinion, at least in this case, because again, it was annotated by humans. It's kind of unfair because a network is trying to mimic a community of humans instead of a single human. So of course it's different than a single human, but is the single human really wrong? It depends. As we saw, like in the cherry Dalmatian picture, like I would have made a mistake. I would have said Dalmatian. Like it was popped up more than the cherries to me. So yeah. Okay, I'll leave this slide here if you want to check. We'll upload the slides as well. This is just a taxonomy of the evolution of this image classification models. So that's it for image classification. But trying to go like forward from image classification. Like for now, we did detection as a classification problem. So we want to see if an object is in an image. But nowadays, people want to do something more. So where is the object in the image? That's very important. Like, let's say, again, it keeps coming up, but you do autonomous driving. You just don't want to know if there's a car in front of you. You want to know where it is. Okay, like there's a car here. Yeah, thank you. Like, where is it? I have to avoid it. So that's very important. So instead of modeling as a classification problem, we can model it as a regression problem. So instead of classifying the object, we can regress where the object is. Okay, something slightly different. So here we have ImageNet, and we have an example on a different image of what this regression could be. So we have this class 1 predicted on this bounding box. Okay, so this output simply says that there is a person, C1, in this area of the image, and there is a horse in this other area of the image, and they can overlap. All right. So this is a completely different problem. It's related, but it's very different. A very popular approach that's been presented in 2014 to do this, and in general, like most approaches were working similarly to this, is to use this RCNN. So R is not recurrent, R is regions with CNN features. So what these kind of approaches do in general, not just this specific one, is that you have an input image, you have some part of the network that looks at the image, extracts boxes that might contain something, doesn't know what it contains, but it looks like it contains something. And then all of these boxes are given to a classification network, which could be AlexNet, or another network that they train from scratch, can be anything. And this network will output the class, okay, for that region. But there is a couple of problems with approaches like this. One is that it's not easy to incorporate the context. Okay, so if you have like the human here, it's very clearly a human, but sometimes you need some context to understand what it is or to have more accuracy for what it is. So usually these networks do not see the context, or it's not easy for them to see the context. And the second problem is speed, because you basically are processing the image twice. One to extract the regions, and then again, you have to look at the image again to get the classes. Okay, so you look twice at the image. You know where I'm going? I'm going to you only look once, which is the YOLO model. This is the first iteration of the YOLO model from 2016. It's still super popular. I think we are at the 10th iteration today, I believe. Sometimes a new one comes up and I forget. But the architecture has changed, but the main idea hasn't. So you want to look at the image only once, and you want this operation to be very fast. So this is the YOLO architecture. It's 20 layers plus 4 layers in the end. So overall it's 24 layers. It's almost all convolutions. You have some 7x7 convolutions, some 3x3 convolutions. In some later YOLO versions, they started using only 3x3 convolutions as well, but they started with this. And finally, they have a fully connected layer here that brings this big feature space to a single latent embedding of size 4096, and then another fully connected layers to get, that's my mouse, to get this output. Okay, what this output is, we'll see in a second, but to get some output. And they use leaky relu activations, so that's the main. Okay, so what do we output from YOLO? Like, what can we do? So the first thing YOLO outputs is this list of probabilities. Okay, so each of these is a probability that that specific class is in the image, let's say for now. Okay, so probably the class 1 plus 2 plus n. So of course, in the end, we can apply a softmax operation between the probabilities to get the one that is present. Okay, is it clear? So we have a bunch of probabilities. We can normalize them to 1 and take the maximum. That will be our class in that region. And then we have other things. So this C1, X1, Y1, C2, X2, Y2, and so on. Okay, so class probabilities. Length is the number of classes. Okay, this C1 is a confidence score. So how confident are we of this prediction? Then we'll see in a second how do we compute the score. And then we have 4 coordinates here. So these 4 x1, y1, square root of w1, square root of h1, these are bounding boxes, okay? So it's the actual box where the object is contained. So x1, y1 is the center of the box, square root of w1 is the square root of the width, and square root of h1 is the square root of the height. Yeah?
What's the difference between the confidence score and the probabilities?
Yeah, so the thing is, we are not computing a single bounding box. Okay, we do not want to just find one object in the image and one bounding box in the image. We want to do it multiple times. So instead of having, let's say, if you want to do it very simplistically, let's not look at YOLO, we could have a bounding box that predicts class scores, and the highest class score is the class that is present in the bounding box. And the score for that class could be the confidence, okay? I think is what you propose. Like, what do we have the confidence if we have the probabilities?
Yes.
Like, if the probabilities are like 0.3, 0.3, 0.4, the network is not very confident. If the probabilities are like 0.9, 0.1, 0.0, then it's much more confident. That is true. But that's not directly what we want to do. What we want to do is that we want to predict different boxes that can contain different objects. And we want the box to predict how close the box itself is to the ground truth. Okay, so not just not just how the network is confident on the class, but also how much the box is confident on the location. It's an overall prediction of itself.
So the confidence score includes positions.
Yes. Yes.
Like, so how do you decide the bounding box, and does it have its size does have effect on the final accuracy as well?
How do I decide the bounding box? What do you mean? Sorry.
Yeah, the size of the bounding box that you need to create. Let's say here's the grid for the particular image, and then you try to decide to predict the scores in them. And
Yeah.
does its size matters for the accuracy of the model itself?
Sorry, I'm
Or
not
it's
sure I
just-
understand the question. So in the ground truth, we have some manually annotated boxes.
Okay. So you would, okay, you fix it there.
Yeah.
Okay.
Yeah, and the
You
network,
fix it at the annotations itself.
yeah, so we have annotations for the ground truth. The network will try to match the boxes as much as it can to the annotation, but we also try to predict a confidence score. We will not compute the confidence score, we will predict it. We want the network to predict it. So there is a way to supervise that. And this, as I said, there's multiple boxes. So in this case, there's B. Okay, I only wrote 2. There could be as many as you want. YOLO V1 uses only 2 boxes. But we don't want like 2 boxes and 1 object in the entire image. So with what this can do is that we have 1 maximum probability class and 2 boxes. That's it. So what this network can do right now is compute 2 boxes, and each box can either contain an object or not, but the object is just 1. Okay. This right now cannot do more than this. So what they do is that they divide the input image on an S by S grid, and they do this for every piece of the image. Okay, for every rectangle, every square in the image. Is it kind of clear?
No, I wonder.
Yeah.
For example, if there is no image, they classify everything. Do they classify every grid, or is it like for this image? Is it like just a dock with label of dock, or is it like every grid is like this is green tree, this is a car? How it works?
Sorry, sorry, I don't understand the question. Can you repeat it?
I mean, when you label this entire image, this entire grid,
Yeah.
I wonder. There will be only one dock, or will it cover also a car behind, a bike, like trees? How it works when you're labeling every grid?
So
Or am I overthinking?
I'm not super sure I understand the question. I'll try to answer. The thing is, let's say we are, I don't know, in this box here, this one. And in this box, there is a piece of the bike. So the box, even though we are predicting inside that cell, the network itself can see the whole image, and the box is not limited to be in the cell. The center, X1, Y1 has to be inside the cell, but the width and the height of the box are not bound by the size of the cell. So we can start from here as the center of the box, but the box can be drawn outside of the cell. Was that the question? Like, okay, cool.
But I get it.
The question is more about the task. So what's the objective for this image? Are we trying to say there's a bike, there's a dog?
Yeah, I would say we would want to say there is a dog, there's a bike, there's a like a van or something, there's a tree, and maybe there's like a little wall there.
It's still objects, it's not pure, it's not pixel by pixel
No.
segmentation.
No, it's not segmentation yet. No worries. So yeah, what's the size of this output? So we have B bounding boxes, 2 in the case of YOLO. Each of them has length 5, and we have 20 classes. Yeah, because they don't use ImageNet, because ImageNet doesn't have the box information. They use another dataset. So the overall length of this output is 2 times 5 plus 20, which is 30. And they do this 30 long output for every grid cell, and it's an S by S grid. And S by S in the case of YOLO is 7 by 7. Okay, you can do it higher resolution if you want. In the previous slide I have it here, you see the output is 7 by 7 by 30. Okay, it's exactly this. All right, so then what do we do with that? So we start with an S by S grid on the input, and for every cell we will compute 2 bounding boxes and a class probabilities and a confidence score for the bounding boxes. So what we get is here as one output of the network, we get the bounding boxes and their confidence, because the confidence is related to the bounding box. And here we have a class probability map, because as I said, the probability is not related to the bounding box, but is related to the cell itself. So you can see this as a segmentation map. It's a very coarse segmentation map. It's not pixel by pixel, it's like square by square, but it gives you an idea of this. Like it's a decent segmentation for the resolution, I would say. We put them together and we get final detection. How do we put it together? I mean, it's a matter of deciding what boxes are good or not. We can threshold them, threshold the confidence. We only keep the boxes that have a higher than 0.5 confidence. And of course, if a box has the center in a specific grid cell, then the class of that box will be the class of the grid cell. And then if one grid cell has 2 boxes and they both have a high confidence, we only keep the one that has the highest confidence. We actually discard the other one. There is a non-maxima suppression here as well. So in the end, we keep these. Okay, in this case, it's the van, the bike, and the dog, not the tree. Okay. Yeah.
Just so that I understand.
Yeah.
Like you have a 5 by 5 grid input,
Yeah.
you give it to the model.
7 by 7, yeah.
Yeah, and then at one side, outputs you the bounding boxes and the confidence scores for those bounded boxes, which has been decided by the annotations that has been done previously.
Yes.
Right, and second, it also gives you the like grid-wise probability scores.
Yes.
And then it's okay.
Yes. Yeah. So now are you really ready for some equations? There you go. So this is the loss function. It's actually quite simple. I'll go term by term because we will see it in the code as well. But before that, let me talk about the intersection over union very quickly. So intersection over union is a metric. So if you have two boxes, we want to get how good they are. Okay. So yeah. So let's say one box is this, like top left, the other is this bottom right box. So how close are these two boxes? Well, we can compute the overlap and divide it by the union. The closer to one this metric is, the better, right? Because we want the two boxes to be perfectly aligned. In that case, intersection is the same thing as the union. So you see here some examples. This is poor, 0.4. This is good, 0.7. This is excellent, 0. I don't see. Okay, clear, intersection over union. Okay, so let's see what the loss does. Let's go term by term. No, disappear other terms. Okay, they don't. Anyway, let's go term by term. So let's take a look at the first one. So we have some lambda, which is just a hyperparameter. We have a summation over S square. So this is for all the grid cells. And this is J from 0 to B. B is 2. So for all the bounding boxes. So these two summations are for every bounding box in every grid cell. We want the predicted x hat I center coordinate on the x-axis, center coordinate and y-axis to be as close as possible to the ground truth. Okay, nothing particularly difficult. This is a mean squared error for the centers. We do the same for the width and the height of the bounding boxes. We take actually a square root, as I showed before, just because the the bigger the width and height, the greater the error. And for mean square error, that means that they impact more. We in general want to the different boxes, whether small or big, to have a similar impact to the loss. So they take the square root because it doesn't make it linear, of course, but it's closer to linear. They saw it works better. Does it kind of make sense? Yeah. So what is this one obj ij? So I think I put it here. No, it's not here. Okay. Anyway, this is an indicator function that takes value 1 if the ground truth contains an object in cell I and box J. Okay. If there is an object there, then we supervise that. Otherwise, we don't. Which means that we are not supervising the centers and the sizes of the boxes that the network outputs in regions that do not have anything. Okay. It's not that we are supervising them to be small or to be somewhere. We're just not supervising them. Okay. Because there shouldn't be anything there. So there is just no supervision there. Yeah.
What the model predict that there is something there? We don't take into account that he made a mistake.
Yes, we do with the confidence scores. So we want the boxes that are wrong to have very low confidence scores, which is what we do like right after. So here, it's a similar term. C is the confidence, and we want the confidence of the boxes predicted to be high when the indicator function is 1, so when there is an object, okay? I say high, so this CI without the hat is the ground truth value for the confidence score. And this ground truth value is this. It's 0 if the cell has no ground truth objects, or it's the IOU if it does, okay? So it's kind of a weird way to supervise the model, because as supervision, it's not that we supervise the model to predict 1 of confidence when there is an object. We want the model to predict the IOU of itself. It's kind of cool. So the model tries to predict its own IOU. The model doesn't know the ground truth. The model only knows its own output, but tries to predict an IOU, which we interpret as a confidence score. The bigger the IOU, the more confident the network is. So this is the way we supervise this part. So when there is an object. This instead is when there is no object, okay? So when there is no object, we want this to go to 0, okay? The confidence has to go to 0. Again, here the supervision is 0. Is it clear on this part? I can go through it again. Don't worry to ask. Yeah. Yeah, of course. So like, don't even look at the loss function. So the network will output 2 boxes at every grid cell. In any case, when there is no object inside that grid cell, we want the confidence score to go to 0. So we supervise a 0 there. When there is an object there, we want the network to output its own IOU. So we use the IOU as a supervision for the network. So we take the bounding box. So let's say there is a grid cell that contains an object. The network computes a bounding box that at first it will probably be bad, but there is a bounding box there because it computes it anyway. We will then compute the IOU between this computed box and the ground truth box. And this will be used as a supervision for the confidence of the network. So we want the network to know that that bounding box they produced was probably very bad, so the IOU was small. If it was good, the IOU is going to be big.
Is CI the IOU?
CI is the IOU, yeah. It's this IOU if there is an object. If there is no object, we cannot compute the IOU, so we just say 0. And yeah, and the final part of the loss is actually very simple. It's just we're trying to make the probability of the classes be close to the ground truth. Okay, nothing particularly difficult here. Again, only if there is an object. If there is no object, we don't care about the probabilities of the network. If there's an object, they do not matter. We just want the confidence to be 0 in that case. Just one thing to add about these hyperparameters. So the reason why they split, for example, this part with this part, they could have been together, right? Like there is an indicator function, there is a C that has 2 different values. We could put them together. The only reason why they separated them is because this no object part happens much more frequently than the object part. Like there's most of the cells do not have the center of the object. It's only one cell that has the center of the object. So they have to use a small lambda no obj here to have this part of the loss contribute a little less. Otherwise, it was too impactful. And the same for the coordinates. This is just a scaling. I don't remember if they had to increase it or decrease it, but it's just to scale it so that it makes sense with the rest of the loss. Is it clear?
Yeah, and does that no object parameter,
yeah,
parameter that would be sensitive to the density of objects in the target set or the training or the data set?
Yeah, it's not a parameter, it's just an indicator function though. So we're not trying to learn this.
The lambda?
Sorry, what? This. Oh, sorry. The lambda is a hyper. Yeah. Sorry, I thought you meant this function here. So this function here, of course, depends on how dense they are, but we don't care. It just impacts the loss. But yes, the lambda it depends on how dense they are. Yeah, how small or big they are. Yeah, depends on the data set.
And are those parameters learned, or they are?
No, they're hyperparameters. So they tested with a few combinations and decided that one worked better than another. Okay, some examples of the output. Okay, yeah, they pre-train on ImageNet, and then they train on this dataset called Pascal VOC, which is a dataset that contains all the bounding boxes and whatnot. They pre-train on ImageNet because they saw this works better. So go back quickly here. They have this all this network. So they take the first 20 layers up to here, I think. So these big convolutional layers, they use this and then they give them a classification output, like a classification layer, and they pre-train all of this on ImageNet. Okay, so this is just a big convolution. It's basically similar to a VGG. Okay, it's called darknet. They pre-train it on ImageNet. And then they remove the classification part, they add these final layers, and then they fine-tune all of this on this Pascal dataset for object. You can say it. Regression. Thank you. Okay, there you go. So these are some results. You can see the green is ground truth, the red is the predicted no, sorry, the red is the ground truth and the green is the predicted. It works. Okay, it's not perfect, of course, but it works fairly well. And this is really the very first approach. Now we've come a long way, but models are getting better at this. But it works, and the cool thing is really fast. It can run on a laptop CPU, no problem. And it could even back then. Well, maybe not so fast, but still could. So here's just a slide I found on YouTube. You see some, the MAP is the mean average precision, so the precision in detecting these bounding boxes. And you see that this, like RCNN, the region-based, is good. It's actually slightly better than YOLO, but it's very slow. You see like 0.05 frames per second, 0.57. This is very fast, sure. But YOLO was 45 and now is even more. If you need to use these kind of things in real time, which you probably do in autonomous driving or robotics or stuff like this, you need the model to be very fast. You just don't need many FPS. You need the latency to be as small as possible because you want a response from the model immediately if there is something. So that's why YOLO has been so important. And of course, since then, it's also improved in performance, in in accuracy. Okay, that's it. Any questions? Yeah.
What do they do to the fast YOLO to be this much faster?
It's mainly the fact that you look once instead of twice. That already saves something. And I believe it's because in the RCNN, I think the classification network is fast, but the region prediction network is very slow. They had to use a big network and it was too slow and they couldn't do it with a smaller one. I think that's the advantage of having a single network is that it all learns how to do both things together.
Okay, but the image is like YOLO and fast YOLO. What's the difference between the two?
Oh, sorry, between YOLO and fast YOLO. Fast YOLO is smaller.
Is what?
Smaller. YOLO is, as I said, 24 layers. Fast YOLO, I don't remember, but maybe less than half the number of layers. I mean, here the MAP is kind of terrible. So okay, but nowadays there is, I think YOLO V8 that I have in a notebook has 5 or 6 different models depending on the size you want. The small ones are super fast, but they're still okay. They're not this bad. They are actually good. Of course, the big ones are much better, but they're slower. Still kind of fast though. I can run also the biggest on my laptop. It's not gonna go at 60 FPS, but I think it goes at like 20 or so. So it's not that slow. And if you have a good GPU, it's going faster. Okay. So demo. A few things. Let's see what we have time for, but of course you can go through the rest whenever you want. So one is this YOLO V1. This is a full implementation from scratch of YOLO V1. The thing is, the original YOLO paper implemented it using Darknet, which is C++ implementation. So this is just a full PyTorch implementation. So it's nice. I took it, I adapted it from this Kaggle version. I think it had a few mistakes. So this should be a little better. I put most of the functions here in the utils file. So we can quickly go through them just to show what they are. So there is a CNN block, which is just a convolution, batch normalization, and leaky relu. As I said, they use leaky relu in YOLO. And then there is a helper function to compute the intersection over union. Can you see on Zoom? Is the resolution fine?
Can you make it a bit larger?
Yeah, sorry. Can you make, sorry?
A bit larger.
Larger. I thought you said lighter. Use light theme on Visual Studio is illegal. Don't make me do that.
The dark mode is okay. Yeah, just make it larger.
Where is it?
I guess it's like maybe Control Shift plus. I don't know the on-market works.
Yeah.
Yeah, thank you.
No worries. Okay, so we have the intersection over union, just a helper function to compute what I said, and not particularly interesting. Non-max suppression, in this case, it simply goes through the boxes, sorts them by the confidence score, removes removes the boxes that have a confidence lower than the threshold. So here it keeps the ones that are higher than the threshold that you specify. And then in this function, really not particularly interesting, simply takes basically the best box for each grid cell and the best boxes in general. Then we have the mean average precision, just the computation of the final score. Some helper functions get B boxes to get the boxes out of the model, to convert the cell boxes from boxes, to convert boxes to cell boxes. The reason is the boxes are usually parameterized as so instead of having the width as the pixel width, they have the width expressed as a ratio between the width and the cell width. So you have to multiply again by the cell width to get the actual width. That's kind of it. Not particularly interesting. Save checkpoint, load checkpoint, always useful. And compose, just because we want to compose some transformation to the images, but I'll show it later. It's not particularly interesting. Okay, then maybe we can take a look at this. So I added this data set, fruit. It contains a training set composed of 480 divided by 2, so 240 images of bananas and oranges. Okay, some fruit. So you see an image here, another here, another here, and so on. And the annotations are in XML like this. So can this move? Yeah. So the annotations are like this. You see, can I zoom? No. Okay. Anyway, you see name Apple. So this is the category, and this is the bounding box. Okay. So the bounding box here in the annotation is expressed as the top left pixel, bottom right pixel of the bounding box. You create a rectangle out of them, and you get the box. So this is kind of it. And then a test set, which is a bit smaller, 1 and 20, so 60 images. So this data set is quite small. Okay, we will try to train YOLO with this. We will get something. Of course, the bigger the data set, the much better it gets. Okay, and you can of course find pre-trained YOLO models on the internet that you can use as they are, or you can fine-tune them on your own task. Okay. So fruit data set, as you can see here, we specify the number, like the grid size, let's say 7, YOLO is 7, and the number of bounding boxes, because we will load this data set in a way that is useful for the network. So we just go through the images, get all the file names and whatnot. In the get item, so we have this class dictionary. We will convert apple to 0, banana to 1, and orange to 2. Yeah, so we will get the, yeah, oh no, sorry, I saw a hand. Okay, so we will find the bounding boxes. Again, we get the x min, the x max, the y min, and the y max. We'll convert it to what we use for the network, which is center x, center y, the width, and the height. We'll append it to all the boxes that we have. And we will actually do this for every grid cell. So even though there is no box, we will load the no box for that grid cell because it helps for the loss, but not particularly interesting. You can do this in any way. You just have to be consistent with the other functions. Okay, we load the boxes, we append them. We can apply some transformations if we want, not in this case. Convert to cells. Okay, yeah, this is the part I just mentioned. So for each label matrix here. So the label matrix has an ij indices, which are the grid locations. So it's a 7x7 grid indexed by this ij indices. And then this last dimension contains all the information for that grid cell. So it will contain the class probabilities, which will be 0 except for the actual class in that grid cell, which will be 1. And and the box. Okay, so here the box is located here at self plus C plus 1, self.C plus 5. The 4 coordinates of the box are placed. And the class label finally. But that's it. And the dataset returns then the image and the label matrix for that image. And finally, I also had a helper function to visualize the boxes in a nice visualization, hopefully. Okay, so let's take a look at YOLO. Just this. Maybe we can start now for like 15 minutes and then we finish later. The segmentation part is a bit shorter, so it's fine. We can finish in the second half of the day. All right, so in terms of like stuff that you need to install if you want to run it, it's nothing particularly crazy. There's OpenCV. Do you know OpenCV? No, so it's a library in computer vision, in general in image processing, not even computer vision. So you can use OpenCV to load images, transform images, do stuff to images. It's a very popular library in, I think it's in C++, but there is a Python binding. So this is the Python binding for CV2. I'll just use it to load the images actually. No, I will not do much with it and to visualize them. TQDM, do you know TQDM? Okay, nice. And yeah, torch info just to print the model and all my functions from the other file. Okay, some parameters, we will check them later. Okay, so let's see the architecture. So this is the configuration of the model. It's exactly the same that I showed in the slide, nothing different. So we have a 7x7 first layer with 64 filters, stride 2, padding 3, max pooling layer, and so on. And we finish with these oh yeah, sorry. The 4 convolutions. It does include the final fully connected layers that will be just added by this class. This is the YOLO class. It will take the architecture configuration, instantiate all the CNNs as specified in the architecture, and then finally create the fully connected layers, which are 1024 by S by S, hidden size, dropout, leaky ReLU, and then the final linear layer from the hidden size to the final output, which, as I said, is S by S times this, which is going to be 30. So 7x7 by 30, the one I showed in the slide. Also, I mentioned that there is a dropout. The dropout for YOLO V1 is 0.5, and the hidden size is 4096. To have it run nicely on this small data set, I will actually use 496 as a hidden size and no dropout. Otherwise, it doesn't really converge. The data set is too small, but in general, so that you know the actual parameters. Then we have a train function. So the train function is quite standard, I would say. We use TQDM, so we get the loader. This is a PyTorch data loader that loads all our data from the dataset, the model, optimizer, and the loss function. So we enumerate the TQDM loop, get the images and the targets. We put both of them to the device we want to train to. If you have like a GPU, you can use CUDA. If you have Apple Silicon MacBook, you can use MPS, which is also quite fast. It's quite a bit faster than CPU, so that's nice. MPS doesn't really have all the support for all the models, but convolution models are fine. So that's cool to use. Okay, then we predict the model output from the input, and then we compute the loss function between the output and the targets. And yeah, and just optimize the model in I think the usual way. I think you've seen this already. Right. Okay, this loop set postfix is just for the TQDM to show the loss. And then we finally print what the loss is. Okay, some more meaty content right now. The loss, finally. So in the loss, I've been a bit lazy. I didn't modify the B part of the original code. So the 2 is hard-coded right now because it was a bit long to implement, but you can implement it yourself. I mean, it's not hard. You just need to remove some stuff and add loops, but it's not anything more than that. And these are the lambda values, the hyperparameters that I mentioned. So for the no object is 0.5, as I said, it's decreased. And for the coordinates is 5, so it's increased, the importance of coordinates. All right, so here's the loss. So we get predictions and the target. So the predictions have this shape. Of course, they start with the batch size, as usual in PyTorch models. The first dimension is always the batch size. And then we have S by S output times C plus B times 5. So this is going to be 7 by 7 by 30. We reshape them in a way that is useful for us. And then we want to get the, so for every grid cell, we will have this kind of structure, okay? We will have the class scores first, then we'll have box 1 information, then box 2 information, okay? It's all flattened. This array has length 30, okay? It's all flattened, and this will contain this information. And every box, so box 1 and box 2, will have a confidence score, X, Y, W, H. I mean, square root of W, square root of H, okay? So what do we do is, first of all, we compute the intersection over union of the boxes. So again, we take the predictions and we want these values, okay? So it's these, okay? Self dot C is the number of classes. So self dot C plus 1 will get this X score.
Dot mean in the square brackets?
Oh, it's so if you have this, do you know? Okay, so having the dot 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 just means you have this like as many times as needed except the last dimension.
Okay.
Okay.
And can you, cool. And can you do that for more, so you can specify k dimensions and then dot 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 fills in n minus k?
Yes.
Okay. Interesting.
Okay. So we get the two intersection over union scores and we concatenate them just because of it's useful. Then we get the max of the IOUs. Why the max? Because again, out of the two boxes that there are in a single cell, so the boxes cannot compute different objects, okay? We only have one class score for the cell, okay? So we have two bounding boxes in a cell, but only one object. We cannot have two in this architecture. So the two boxes, one is going to have a lower confidence score, the other is going to have a higher confidence score. We just want the higher one, okay? We don't care about the low one. The reason why it's still useful to have two is because they kind of get specialized to do different kind of things. One maybe for bigger objects, one for smaller objects, maybe one predilects one class, the other another class. So it's still useful to have more than one, but in the end, we only care about one. So we take this max operation, we get the max IOU and the index of the best box out of the two. It's plural here because this is actually a parallelized operation for all of the grid cells, for all of the images in the batch, okay? Because of this, okay? This basically parallelizes the operation on all of the images in the batch and all of the grid cells. All right, then we compute this indicator function. This is again, the indicator that is 1 when there is an object and 0 when there is no object. So to do this, we check the target, in this case, not the predictions, and we check this self.c. At this location in the target, we have the presence or absence of an object. Before, when we loaded the data set, we would put 1 right there when there was an object and the 0 when there was no object. So we do this. All right, and then we have all the different parts of the loss. So this part is for box coordinates. Then we have this part for the object loss, so the confidence score. This part for the no object loss. So again, the confidence score when there is no object. And finally, the class loss for the class probabilities. Okay, and then the final loss is just a summation of all these terms. Let's go through them. So in the box coordinates, we see that let's take a look just at this part for now. So these are the box coordinates of the second box. These are the box coordinates of the first box, okay? We take them from the array, the predictions array. we multiply them by this best box index. So when the best box index is 1, it means that the box at index 1, which is the second box, will be best. When the best box index is 0, it means that the box 0 is best. Okay, so by multiplying box 1 times this and box 0 times 1 minus this, then we get the actual prediction for only the best of the two boxes. Okay. Again, this is because there's 2. If there's more than 2, just loop this operation, check which one is the best, and do this only for the best box. Okay, this is the only thing that matters. So these are the box predictions for the best box only. We multiply them by the indicator function because, again, we are interested only when there is an actual object there. Otherwise, we don't care. So this will be 0 when there is no object, and we don't care anymore. We do the same for the targets. So we multiply the targets also by this, so that we only care about the target locations when there is an object. When there is no object, target locations will be 0 because we didn't load anything right there from the annotations. But we multiply this anyway. Then we have to take the square root, as I said, because we use that. So we take the square root of the absolute value, and then we put the sign out of the square root, because otherwise we cannot do the square root. And we do the same for the targets. We put everything together and we compute the mean square error for the coordinates. Okay. It's kind of clear.
Why do you have the one in -6?
Sorry. Here. I know it's a 1/1,000,000th. Like, yeah. It's because of stability. We don't want to have a complete 0 here, I believe. This is Actually, I don't know why they use it here. I need to check, but it's a term that appears often when you do this kind of operations, because you usually don't want stuff to go to 0. Otherwise, it makes it difficult to supervise. But I need to check what happens in this specific case.
For the general idea,
Yeah.
So exact 0 is a problem.
It can be, so it can be a problem. Let me think. So having an exact 0. Wait, this is because of the width and the height. So, I mean, it cannot really be 0. But if it's a 0, oh, it's not differentiable. That's why, because we are taking an absolute value here. So since, okay, we are computing a square root, but the output of the network is not guaranteed to be positive. It could also be negative. It will be positive in the end, hopefully, if the network learns, but it can be negative. So, and it can be 0. So we don't want this thing to be 0. So we add this so that it's not 0. If it's 0, this operation is not differentiable at 0. So the gradient doesn't flow. Yeah. You could compute a subgradient in that case. Okay, anyway. Okay. Object loss. Okay. Yeah, okay. So we do this like best box times the prediction and y minus best box times prediction to get the predicted best box coordinates. And then we multiply it by the indicator function, and then we take the IOU maxes. So we use them as supervision, as you see. Okay, so we take the mean square error between the confidence score predicted and the IOU computed right here. So the IOU is not in the annotation, okay? In the annotation, we only have the box. We get a box as an output from the network, compute the IOU between that and the annotation, and then we use that to supervise the network, okay? In a way, this is self-supervised, in a way, because this information is computed. Then here we have an annotation, which is the box. So it's not, the overall approach is not self-supervised, but this specific part is, because we use, so it's a supervised method because we have supervision, but we do not create it manually. This is computed. It's a fine line. Sometimes you can define something as self-supervised and people don't agree, and vice versa. But in general, yeah. Then we do the same for the no object loss. It's absolutely the same thing, but instead of having this IOU here, we have zeros, okay? Because when there is no object, we want the confidence to go to 0. Absolutely the same thing, just a 0. Yeah. Oh, mean squared error. So as you saw in the loss, we take like the summation of all of the terms, we square them. It's just a mean square error, which is what this computes. So we don't have to do it ourselves. Finally, the class loss, which is again a mean squared error between the predicted classes and the ground truth classes. Note that they did not go on a cross entropy loss here. This is a classification task. They could have gone for cross entropy. They decided not to. I guess it works better without the cross entropy in this case. But you could go with different loss here. This is just a prediction of classes, so you could go with anything. Okay. It's 11:58. I would say let's stop. I'll show briefly the rest and then run the model a few times to see what happens in the afternoon session. That's okay for you, because I'm hungry as well. All right. So see you later.